Okay, if you are ready, I'd like to start. I apologize again that I have updated the slide that you have now. So I will send to you the updated version later. But for today, please look at the slide that I distributed to you. And today's lecture is focusing on regulation, signal regulation. This is very, very, very important thing in a theoretical aspect. Last week, we have discussed denoising. Denoising is very important for the practical use of the signal processing. On the other hand, regulation is quite important for theoretical aspect of the signal, because through that technology, we can model the signal, which in other words is to understand the rule hidden in the signal. Okay? So let us start from the very beginning. In the previous lecture, we defined that the signal is the data which is associated with index or indices. And in this lecture, we're going to use the same definition. So here and there, okay? And the main topic of this lecture is discussing the relationship between two signals, okay? The first signal is independent signal in terms of the relation. And second signal is dependent signal, okay? Which means that like the index itself, that is the signal. So the signal itself can be represented by here, like this, in terms of the observing data. And this is the independent signal, which in this case may be location or time, I guess. Or in other words, index of the signal. And the height represents the magnitude of data, value of data. So there are two random variables that is regularly distributed independent variables, and also variable, and also the dependent variable. So in analyzing the relationship is the main focus. For instance, you know the linear regulation by the word, okay? If they are correlated in linearly, then the global shape of the data should be something like this, just like we saw in the population growth of the Nagoya city here. Okay, we saw that the time and the population of Nagoya city are in somehow proportional in this at least area, and the nature of the proportionality is linear. Okay, so if time goes, then the population increase, and the speed of the increasement is somehow constant. But this is a very simple relationship between one variable and the other variable. Okay, so we're gonna say something about this relationship based on the model fitting. Okay, model fitting is the way that we will understand the hidden rule behind the data distribution. これ聞こえてますかね? So this is a quiz, okay? What do you put? Which number do you put here? Are you? What? 314, something 5, blah, blah, blah. 1. Why? Yeah, you're right. Okay. So we have a lot of signals in everyday life. And say, for instance, the pi can be represented by a sequence of numbers because that is an rational number. And 31415, blah, 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 is a sequence of the data, digit, and that represent pi. So if we knew that this represents pi, then we can easily find the value here. What is this? So knowing the rule behind the sequence gives you a guess, reasonable guess to the unobservable kind of things, or erroneous data. So the signal regression is something like that. So regression of signal is a problem to find the rule, okay? That generates the signal or ordered data, in other words. The rule is useful when it is represented by a mathematical form, like pi, in particular by a function, okay? So if xn is given by a function of n, then you can further generate data until it becomes a very, very large number. On the other hand, if you understand that this is a sequence of pi, it's still not very easy for estimating or for predicting the number in 100th index. So function is good. You can calculate the value, like 15 over 2 pi over 15 times n, cosine, blah, blah, blah. Okay. So what is a form of the rule is an open problem. We don't know the form of the function, even if we knew that the xn is a function of n. So that's a very important point. That is open. So when the answer is not clear, we may say, hypothesize a rule, okay? Let's hypothesize that this signal has this sort of nature, which mean that periodical in a sample of 15. So the periodicity of the signal is 15 samples. So that is a hypothesis. We don't know, because what all we see is only data, not this function. Okay, we measure and try, and we're gonna have a large amount of data, but still we cannot see this. This is the only result of our hypothesis, or in other words, intuition. Okay. So if you have a good eye, good sense, then you can correctly hypothesize the rule. But if you have bad sense or bad experience or extraordinarily different experiences from your life, your guess may be quite different. But God knows, we don't know exact form of the rule. That can only be hypothesized by us. And in other words, we sometimes say model. We're going to model the time sequence signal by means of cosine sinusoidal function. That is a model. Hypothesis or model are quite similar idea. Let's think this phenomena, that obeys like this equation or formula. That is modeling or hypothesizing. And most important thing after that is to confirm the correctness of the hypothesized theory or model equation. So this is a whole I like to talk today. So the discussion becomes the question: what is the good rule behind the data? What is the best rule or good hypothesis? That is one big question, okay? And it may be natural that the error due to the hypothesis with respect to describing the data sequence which is observed is one very good measure for evaluating the model or hypothesis. Maybe I'm going to use the word model later. But okay, the goodness of the model is evaluated through the error. Okay, this is a model which is proportional line to the n. And these are data. This is the realistic data, your observation. And goodness of your guess can be measured by the error value. If the error value is very big, then your model might be somehow different or not precisely describe the situation. And each individual error is random, actually. Mathematically, in mathematical sense, it is random if your model is very good. Otherwise, error becomes biased value. Well, anyway, you can not easily evaluate the goodness of the model by small number of of the evaluation samples. You can use a lot of numbers of evaluations and sum up. So this is a very, very typical equation or term that's gonna evaluate the goodness of the model. This is the model. The value of xn is some proportional to the number n plus theta 0. So here are two parameters. One is theta 0. Is a model parameter, and this is another parameter, theta 2. So they sometimes use the notation largest theta, which has two parameters, theta 0 and theta 1, has a model parameter. Model parameter. So this is very important idea. There are two aspects. One is hypothesize that this n and xn are proportional, linearly proportional. That is the first idea. And second idea is that going to be written by this, and how do we defining or how do we finding the best theta 0 and theta 1? That is the second problem. Model, hypothesize, and estimate the model parameters. Those two things are should be done for solving the regression problem. In other words, obtaining the mathematical rule for representing the data distribution. And of course, you're going to sum up all these squared errors. Yeah, this is error because this is a subtraction of the real value. From real value and model value. There's a difference. And if you square, the value becomes a positive value, and you're going to accumulate all over the data. Then whole data errors can be easily enumerated. And the problem becomes much more technical. How can we find the theta 0 and theta 1? There's only two unknown values, with respect to the minimum error. Okay? So xn, don't forget, you can measure this. Okay, you can measure this as many times as you can. And n is associated value. Therefore, you know n. But you don't know theta 0 and theta 1. So you need to decide theta 0 and theta 1. This is a very fundamental problem. And actually, this is a quadrature problem. Quadrature problem is represented by a second order equation or terms. Do you know, I think many of you have studied about the quadrature form of the function. That is x squared plus a x plus b, for instance. And it can be, how do you say this in English? I don't know. We call this in Japanese 平方完成 or no. A plus b. This form gives you that. If this equation or terms is in the second order quadrature, polynomial. Huh? What? This? Polynomial what? Degree? Is that what you say? In English? Okay. So I mean, do you mean that the conversion process of here and there is polynomial degree? No. Uh-huh. This form is called polynomial degree against to this. Both of them are same. Oh, I see. Uh-huh. Okay. Yeah. We sometimes say that converting this to this form is 平方完成. This is very common, Japanese word for junior high school student for teaching, technique for the entrance examination of universities. So but anyway, actually, when I was a high school student, we don't use that word 平方完成. But anyway, thank you very much. By the way, so this means that we have a minimum value when we change the value of x from minus infinity to plus infinity, because this function looks like this, has only one point, which gives you the minimum value of the total this. So we can easily, solve the problem due to its convex characteristics of the problem. And actually, we do not do this. Usually, we do much more simpler method, which is just taking the derivative of the total error with respect to the theta and put that is equal to 0. Because in the bottom of the curve, we know that the derivatives becomes 0. So the problem of learning the theta 0 and theta 1 becomes a very simple problem. If it has a form like this. And its fundamental procedure is to minimize the total error. Okay, and this is a simple math. Here's an error function, and if you calculate the derivatives with respect to theta 0, the form becomes like this, and you can say that the value of the derivative becomes 0 at the optimal theta 0 value. And also, if you take the derivative with theta 1 and do the same thing, and this gives you the optimal theta 1. And of course, we have two variables. Therefore, we can simultaneously solve these two equations. That is a simple linear equation problem. By the way, you should be careful about that. This value, and taking a derivative of this value sometimes, very tricky because after summing up, you can calculate the derivative, and also, by its mean, you need to derive this function, take a derivative of this function after summing all terms. But mathematically, almost correct that order of the taking the sum and taking the derivative can be replaceable, interchangeable. So you can first calculate the derivative and then do something. Calculate the sum. That is also true. So by taking such a property, we can very much simplify the equation. So I don't know how fast you can calculate this in your brain, but believe me, the result becomes like this. Here's a simultaneous equation for the theta 0 and theta 1, and the coefficient of the each term is like this. Here's a sum of the index from n equals 0 to n minus 1, and is averaged over the number of the samples. And here's the average of the xn. And also, this is the average of the n times x. This is very important term, close term of two variables here. And this is a quadrature sum of the index. And this is the same thing. So if you write down this relation or equations in a matrix form, then you can get this. Okay? So if you can invert this function, this matrix, and I believe that you can invert that, then you can multiply the inversion of this matrix from the left-hand side to the right-hand side of the equation. You can get the optimal theta 0 and theta 1. This is simple math, although it looks very complicated. Say, for instance, this, if you say this is A, then you can get theta 0 and theta 1 is equal to A inverse times this vector. So it's very, how do I say? We are very lucky because solving such complicated problem can be systematically, solved based on the linear algebra. Linear algebra is one of the simplest, subject of the mathematics. Of course, we need to assume that this matrix has an inverse matrix. But actually, it has in almost all the cases. This is what you have studied maybe in your physics class of the high school, or I don't know, in an elementary course of the college. But it is slightly, sophisticated in the notation system. So what I want you to remember as a procedure for solving the regression problem is very simple, and what you can see in one slide. Okay, so please watch these equations and the procedures to solve this problem carefully. Okay, it's a very, very simple. In this particular problem, we can organize two or one matrix and one vector. You see? And one matrix consists of two lines. First line consists only of one. For the n, the capital N, length. And the second line has the ordered number from 0 to n minus 1. That is all we need to prepare for the matrix X. On the other hand, vector Y is exactly the same, or is the signal itself starting from 0 to x minus 1. N minus 1, and x0, x1, x blah 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 blah, x n minus 1. Okay. Yes, T is transpose. Sorry. Okay. So yeah, please be careful. I use T for the transpose. So which means that X matrix has the form like this: 1, 1, 1, 1, 1, and 0 to n minus 1. And of course, Y is like here. In order to save the space, actually, okay, what is? Is okay? Huh?
Y transpose, actually, it's a column.
I see. Yeah, I see. Yeah, column vector, yes. Yeah. And also, because this is very, spatially effective, efficient to write this way. Otherwise, I only can, write one or two matrix in a slide. So please be careful if I put T here, which means that the transpose of the matrix. And this is the first step that you need to do. And after that, actually, MATLAB or R, whatever your signal processing tool, does everything. Thank you very much. What do they do? What does it do? It's very simple. Calculate the multiplication of the X transpose times X. Okay? So this times this. Okay? And which gives you a 2 by 2 matrix, because this has two columns, and this is the number of the row is 2 and number of the column is 2 here. Therefore, 2 by 2 matrix. That's going to be your X transpose times X times theta. Theta, I need to mention about theta. Theta is theta 0 and theta 1. Again, column vector or column matrix. And X transpose and Y. Okay? And you can confirm that this product is exactly equal to this matrix. You see? Do you agree? So can you calculate this simple product by your hand for your practice? Let's go. If you have a note or pad, please calculate this product of the matrices and confirm that the result is exactly same with this. Okay. So knowing this is quite, important and make your life easier. You see? あれ、はい。これ？
そこと上で同じ式を行列に直してほしいですね。
これとこれとこれ？
上だと1個じゃないですか。
うん。
それ下だと同じ場所に n が入ってるんですけど、上と下このページって上の2つの式を下の行列式に書き換えてるんですよね。
Yes.
同じじゃないとおかしくないですかってことですけど。
あ、これがね。あ、そうだね。あ、そうだね。あ、そうだね。これ間違ってる。Thank you. I calculate and confirm that. Because this is very universal method, so you're going to see later almost all kind of data fitting, like if you know about the word SVM, support vector machine, or kernel method, all those things use this linear algebra. So if you are familiar with that, you have a great merit with that. Okay. Are there any other errors? No? Okay. I hope you could confirm that. But, time is up, so I'm going to go forward. So again, this matrix is very important, and this is called the covariance matrix. This is known as covariance matrix of the two independent variables. And things like that. So, as I said, this idea can be easily extended to more complicated hypotheses or rules. Here, I used very simple linear relation to model the data. But that is not sufficient in many cases. So what we do for extending that idea is to use the functions like this, and polynomial or linear combination of functions for the data rule. For instance, you can generalize this to something like this: theta 0 plus theta 1 x n plus theta 2 x n xn for square. This is really polynomial, regression, x cubic, blah blah blah. So of course, this is a part of this, and you can extend this in a higher order of the polynomial, or even you can use more general form, like here, which is theta 0 plus theta 1 times phi 1, which takes the value of xn as an argument, and also theta 2 times phi 2 xn, blah, blah, blah. And this function can have, arbitrary form. So this, by the way, is also called linear regression of the data. Although this function can be a nonlinear function, but these are linear functions. And calculating the theta, theta 1, theta 2, again, is the problem based on our hypothesis. And this can be also done very simply by doing the same thing that I show you, or that you confirmed several minutes ago. So here's the formation. Okay, so ym and xn, these two variables are mutually dependent. And in the previous cases, I used simple n, order number, as a signal xn, and I wrote the output or dependent variable using xn. But here I introduced a new signal yn, and these two signals xn and yn are related with this linear form. This is linear form because I am intending to show a vector like here by theta, capital theta. And this function is also, this capital theta is also, capital phi is also represent this. But in this case here, the transpose. Therefore, this is column vector. Okay, so this end up with the form of the previous slide. So maybe you can understand the meaning of the example. And this is very, very typical example that I mentioned in the previous slide, is a multinomial regression. And okay, so if you know that these notations, then we can do the same thing. By the way, this is the merged polynomial regression result taken from the very famous book. Probably some of you have studied that book written by Bishop. And for instance, if the m is equal to 1, in that case, this is simply line. But if m is equal to 3, then it has a 3, how to say, third order polynomial, which means that we have two, curve steady point, and like this. And therefore, I don't know. First, you see this data distribution or signal. Which kind of intuitive model do you have in your mind? I guess that is a very big discussion on which is better model, this and this. Actually, we're going to discuss it later. Obviously, the error value is larger here than this. Yeah, but, we do not know the underlying or hidden true rule in almost every cases, in almost all cases. Therefore, we cannot simply say that this is better because of the model error is less than this. And that is a very important discussion. But anyway, we have flexibility to express the model based on this linear model by using a different order of the polynomial. So this is an extreme case that if you have a very flexible function like a 9th order or 10th order polynomial as a function, then you can easily find a curve that can go through the all data sample points easily. But obviously this is too extreme to understand the hidden phenomena. It is not true because this is one shot of the observation, and that is not always same. I'm afraid that I skipped something. Sorry about that. Oops. Probably, do you see some other slides? Just after the, oh, なんだこれ。あれ。なあこれ。お。ちょっと待って。Something happened. あれ。何これ。So, can anyone solve my problem? I think there's a slide, but I don't see that slide. This is on page 4. It's trouble. No. Let me close first. I cannot close even. Sorry about this. Yeah, what I wanted to explain was the same thing can be done for this formulation. Yeah, this. Oh, yeah, I hate. Okay, sorry about this. Okay, let's start from this. Here's a generalized linear regression based on the unknown function or arbitrary function theta phi 1 from phi m. And you can do the exactly same thing just before. You also put 1 here. Again, this is the X transpose matrix. You're gonna make this 1, and then you're gonna calculate the function value for the function 1 with respect to the first input data x0 and second input data x1 and final input data of xn minus 1. All those values will feed to the function phi 1, and the result value is put here in the second line. And so the third line, you do the same thing for the new function phi 2 and blah, blah, blah. And finally, you're going to do the same thing for the mth function phi m for the x0 to x. So this is a simple matrix which has size of m times n. Okay. So m times n matrix. It is actually transposed form, and if you calculate the transpose of this, you're gonna have the quite same relation that we saw in the previous slide. And here's the y. Y is simple. It's just simply put one line from y0 to yn minus 1. Okay. Again, if you organize these two matrices, or one matrix and one vector, then everything will be done by MATLAB or R or other tools. This is very simple. They calculate the quite same thing, x transpose times x, and then calculate its inverse and multiply it to the x transpose y, which gives you the best parameter theta. So I think you understand the system. So this is quite easy, mathematics. And you should know about this simple math in order to use any sort of regression. It's, that's what I like you to know about the regression. And I'm sorry, I skipped this, but again, we need to discuss the complexity of the model and how can we, find the optimal order of the regression equations, or in other words, freedom of the model. Freedom of the model. Or maybe degree of freedom. Degree of freedom. So if the model has more parameters, then we can build very funny shapes like we saw here. But of course, this is overfitting to the particular data samples. This regression system doesn't work for the different observations. Even the same system or phenomenon are observed. So the defining the optimal order of the polynomial is one of the hot topic, and probably some of you have studied about how do we solve this problem. And roughly speaking, there are two ideas. One very efficient idea and easy idea is to increase the number of the data. You do the observation again and again, then you can get a lot of samples, and trying to fit the rule against those a lot of many samples, then you're gonna naturally close to the real rule. This is almost always true. So if you are not sure, you can repeat the observation, experiment, or survey. That's a very important thing to have a relevant result or simpler rule. In this case, here's a m is equal to 9, which means that the complexity of the model is just same as this. If you use the only one shot of the observation, you get a reasonable one. But if you increase samples to 100, then your result may be pretty good. So please do not, think that it is too tedious to increase the number of the samples. That sometimes helps your life. And this is another sample, okay? So increasing the size of the data is good compromise for many cases when you have no idea on generalization rule, or generation rule, I mean. And the second idea is more sophisticated idea that is regularization. I know some of you have already familiar with this idea, regularization of the system. It is very simple, again. We add one term here to the original measure of the goodness. What is this? This is the regularization term. In this case, the regularization is given by the sum of the, not sum, but norm of the parameters. So please do not forget that theta capital is a vector. Therefore, this is calculated by this. Theta 0, theta 1, blah, blah, blah. Theta 0, theta 1, blah, blah, blah. And because of this, when theta has big norm, then the goodness of the model becomes less. Okay? So we need to understand this term. What is this? This represents the model complexity, actually. Suppose that very extreme case that theta is 0, nothing. Then this is very small, 0, minimum value of the absolute value of square. And if, for instance, the value is concentrated on theta 0 and theta 1 only, and other terms or other higher terms like theta 2, theta 3 are very small. Then this value becomes smaller than the case that all of, say, 5 theta has relevant values, obviously. Therefore, if you put this term and the system tries to minimize this term and also this term, that going to try to find the good compromise between the complexity of the model and error of the model. If the number of the theta which should be used for modeling is smaller, then this value becomes smaller. But in general, if the value or if the degree of the freedom of the system is lower, then the error becomes higher. So there's a compromise. And we have, unfortunately, magic parameter lambda here. And without changing this value, it is not, it is not good as we expect. So we need to balance this error term and also complexity term. And this is the simplest formulation, but its variational representations are very common in a textbook, like non-parametric base and such things. And you can further study about this. But one thing I like to make you understand clearly is that we need to balance the model accuracy and model complexity. And this is the one way to do that. And here again is the result of the compromisation. Again, in this case, I guess we have a large number of the freedom, a large number as a degree of freedom of the system. But if you use a very big value of lambda, like 0, like 1, log of lambda is 0, which means that lambda is 1. Then the weight is too large to allow the good accuracy of the system to have more complex form. Therefore, the result you get is like a line. But if the lambda becomes smaller, which in this case, log of lambda is minus 18, that is far small against this, then because when the lambda is small, then the penalty for the complexity of the system becomes less. Therefore, it allows to use a more complicated shape of the fitting curve, and that is another result there. And in general, this is very interesting idea. The performance of the system with respect to the training set or data set that you're going to fit, or that you have fitted to the parameters. And performance to the unseen data, new data, resultant like this. So if the model parameter, the penalty weight of the model complexity becomes larger, then the performance to the, wait. The performance to the training set becomes, sorry. This is the error, so the bigger the worse, okay? So if the complexity is more emphasized against to the accuracy, the error becomes also, of course, increasing. But the difference between test and training is not so big. On the other hand, if the penalty to the model complexity is very small, then the training data can be, almost perfectly, fit to the system. Therefore, the error is very small. But when it is applied to the test data, unseen data, the discrepancy is very big. In other words, the error is very big. So we need to find, good compromisation, to the test data. So you're gonna try and find maybe here and there. These values are better vary. But unfortunately, we cannot calculate lambda value, which is optimal to the given data set. That is open problem. So it is always very good idea if you like to do these kind of things. You separate your data into 2 sets. And the first set is used for building such model. And second set will be used for evaluating that model. That is a very good idea for practically using these things. Okay, almost all things that I have told you this 1 hour can be done through any kind of mathematical tools. So what you need to do is to do experiment or survey and understand the data. In other words, have an insight of the data and hypothesize a model. And then people do machine, computer do something and gives you a concrete result of the model. But if your idea and way of the confirm the correctness of your hypothesis is not good or poor, then you're gonna reach to the finally reach to the completely different goal. So please be careful about that. Yeah, computer is very useful tool, but in sometimes it is not, verbose, where you cannot discuss with computer with the result. Okay. And another topic that I had with these slides is linear prediction, predicting the future value. That is part of a regression problem because it has quite similar shape of the linear regression, right? So yn can be described in terms of the linear combination of m functions. That is the linear regression that I showed you. But when you change the yn or replace the yn with xn, and also replace the mth function of xn is m sample delayed version of x, right? Then these terms are terms associated with the past value of the xn, and this becomes the current value of xn. So current value of xn is given as a linear combination of past values of xn. That is the prediction problem. Knowing the past value and predicting the future value. That is a prediction problem. So we can formulate that prediction problem with the same setup of the linear regression. That's the point. Okay, this is so-called linear prediction method. Here's a form. We have xn, which is described with the combination sum of xn minus 1, xn minus 2, blah, 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 x minus large m. In the different representation, system line block diagram, you can show something like this. xn will be feedback to the input side with the delay element like this. So we're going to delay theta 1 and going to be feed again. We're going to delay theta 2, delay at 2 steps and multiply by theta 2 and feedback to this, things like that. So these feedback loop of the system can be characterized by the linear linear prediction form. So again, this is a fundamental form, and this is the replacement with a formally studied way to calculate the parameters of the linear regression systems. Therefore, again, we can compose the transpose matrix xn like this, starting from 2, ending from n minus 2. I'm sorry, this is capital N. Starting from 1, ending at capital N minus 3. Starting from 0 to n minus 4. These are all of the same length signals, stacked at the matrix form, and also the original data, which is xn. Here, so xn, xn minus 1, xn minus 2, and xn minus 3. These are actually what you see now. So by calculating the x transpose times x, you're going to be having a covariance matrix here, or autocorrelation matrix, in other words. Here's a so-called autocorrelation matrix. What is R? I'm going to talk to you later. But R is the autocorrelation of the signal x. And also, here's another R. I should discriminate this R and R, sorry, but this is the R, another correlation, but that is cross correlation x and y. So to be more strict, strictly and discriminative, I should write here xx and here xy. Well, anyway, what is the autocorrelation? This is a fundamental, actually idea of the signal processing in time domain. By definition, that is given like here. That is the product of the, expectation of the product, x, time at x, n, and time at m. So usually, if the signal is stationary, then this value doesn't depend directly on n and m, but the difference between two time steps, n and m. Therefore, it can be rewritten like this. The average product value of the two samples distant in k samples, two data distant in k samples. That is the autocorrelation function. Therefore, obviously, when the k is equal to 0, or in other words, the correlation or product with yourself, the data itself, in other words, xn times xn is the biggest. And as the k increase, then in general, the autocorrelation value becomes less, because it is distant data. Therefore, the relationship between current data is very small. And from the data, you can calculate a good estimate of this statistic value by simply calculating the yourself and delayed version over yourself or over n sample time period, and then divide by k. This is a very good estimate for the autocorrelation. And you see, this is what you see here, like here or like here. In this case, x times y, and in this case, xx, and this is xy. Okay, so what I like to say is that calculating this matrix is very easy, and let MATLAB do this. Again, all we need to do is to form this matrix and vector. That is enough for solving this problem in practical situation. And finally, you get the theta, and once you get the theta, then you can predict what you're going to have in the next step based on the previous data, because you know theta 1, theta. But also, it is very important to know that this is the case that the current data is somehow associated with the previous data. In general case, it may be true, but we also know that very special case, which is completely random, sample by sample. It doesn't depend on the previous or past data. for such processes, we cannot use this method. Or if we use this method, the average error is almost the signal power itself. So, but anyway, linear prediction is another version of linear regression. Okay. So I again used almost time for the first part. Actually, I would like to talk next about the regression or prediction for the random process case. So I need to speed up, but let me try. Okay. Last week I talked a little bit about random process. Random process is a set of random variables indexed by time. So here's a set of signals, a set of data, but these data are of course ordered by an index, and this is also a random variable, which means that you cannot know the value before observation. Okay? So the probability of a realization of a random process, okay, you try 5-second measurement, gives you 10 samples of data, and that almost stochastic or random process, then the probability that you sample or that you get such 100 of data is described like this. Okay, this is complicated, but please be careful. F is the distribution function. Okay, you may know about the probability theory, and in the suffix of the F, we usually write the random variable's name. There are n random variables in this case: x0, x1, x2, xn minus 1. And you're going to parentheses here, put parentheses here, and write down the actual number. This is the name of the variable, and this is the value, actual value here, okay? And x0, x1, x large n minus 1. What does this mean? Is that this is the probability that the first random variable takes the smaller value than actual value x0. Say, for instance, this is 3, and this is random variable. Say this is random. The random variable is less than 3, and also, because here's a comma, which means that all those conditions should be met simultaneously, which means that x1 is less than or equal to the actual value x1, and xn minus 1 is less than or equal to small xn minus. So this notation represents the idea of the random process very clearly. We have a number of random variables, and that is ordered, and also that is, or each of them, of course, is, of course, has a property of a stochastic variable, like a distribution function, or density function, or average value, or expectation, or things like that. Okay, so this is a typical, example of what you think about the random variable stochastic process. Here's the 3 realizations of one stochastic process. Even the stochastic process is same. Of course, that is stochastic process. Therefore, you have different realizations of them. And here's like this and this and this. Each individual values are different. But what the most important thing is general or global trend are somehow similar because it is generated from the same random process. So it has a decreasing property against to the time index. That is one, typical property of this random process. What you need to do is by seeing these kind of things and understand the property of the data. For instance, suppose that this is the time, year, for instance, year 0 to year 35. Okay, let's say this is the age, and this is the, how do I say, maybe weight of the, weight is not so. So voice, loudness of the crying voice. Okay, and this is the one subject. This is another subject. You have a lot of data, and what do you conclude is the most important thing in your research. Okay, so someone say that because of the 10, for instance, after 10, or before 10, you don't see the loudness of 1 in all of 3 subjects. Therefore, children's voice is very loud until its age of 10. But that simple, that is a, how do I say, oversimplified conclusion, obviously, right? So, and also it is not easy to utilize such knowledge for the practical use, for instance. So we need to find the hidden rule again behind these observations. And of course, we can use regression method that we have studied. And also, we can do several different things. But anyway, understanding the stochastic process is quite, common in our daily research and development aspect. And for instance, actually, I sampled these data, 3 data based on this line. Yeah. And if you are very lucky and clever and good at skill, then you can guess this smooth line as the rule behind the data. That's the main job of the data scientist. Okay. Because time is very, very limited, I like you know simple one idea, n-gram. I'm gonna talk about n-gram and then conclude this class. N-gram is quite powerful idea based on the stochastic process or probability process. Okay, you may remember the Bayes rule. This is a very fundamental rule, which says that A, comma B is equal to P A conditioned by B and PB. You can change some things, but this is a Bayes rule. And the other rule is a chain rule. That is also very important. Suppose that W1, 2, 3, 4, 5 are the random process, which means that order is very important. So we can rewrite based on the Bayes rule. This probability can be represented by P W1, W2, W3, W4. That is a condition of calculating the W5, and P also W1, W2, W3, and W4. So here's a B here, and here's a A here. So this and this will give you the true probability of the sequence. And you can again expand this probability like this, PW4 conditioned by W1, W2, W3 times P, W1, W2, W3. In short, in the theory of probability process, a stochastic process, you need to think about all sequence. You need to remember the very long path, in order to calculate the sequence probability, and which is, quite difficult. We do not have a long memory, and we cannot use a lot of parameters to predict the very far future. And one very clever idea is to assume that this this assumption, this is very clever. We forget the day before yesterday. This is first day, right? Friday. Oh, it is Friday? Thursday? But Friday is holiday. Okay, thanks God. Okay. So we forget last Sunday, last Saturday, last Friday. But we have some feeling of the yesterday. You can clearly tell that what you did in yesterday, but the day before yesterday. Do you remember what did you eat for the dinner the day before yesterday? What did you have for dinner? I cannot remember. After since I was in the age of 50. Okay. Okay. When you have. Okay. So this is true. I cannot remember what I had last Sunday. This is aging, right? Okay. But anyway, so forget about the very long past, but just current or one step before. So suppose that the probability that we have, the signal W5 at this moment only depends on the one step of the sample, like W4. And all those three data or three observations should be disregarded for calculating this, which gives you a very simple way to calculate the probability of the stochastic sequence of very long, lengths like this. So, when you apply the chain rule, you need to remember still a very long history, but when you assume the Markovian, characteristics hold for this calculation, then what you need to do is to multiply this pair of the conditional probabilities. You see, the probability of W2 by conditioned W1, and probability of W3 conditioned by W2, and blah blah blah. In other words, has a one-to-one correspondence between previous and current. So these characteristics of the sequence is called the Markovian characteristics, and in other words, we call this Markov model, as you know. And we have a lot of different versions of the definition of Markov model. Sometimes we very familiar with this kind of a network graph, which represents that you have a state, and in each state you have different probability function for the observation. But within the same state, the probability distribution is same. And suppose that when you do something observation, and then the state depends on the previous observation, then you're going to move here or stay here and do the same thing again, which is completely the same meaning that you're going to only see the previous sample. Okay, so this is very easy and very useful way. In fact, speech recognition uses this a lot. And of course, natural language processing heavily use these kind of things. Okay, so simply wording, we have special word, unigram, bigram, and trigram. Trigram is a the relationship among three samples, n-1, 2, and n-1, and n. So these time sequence can be represented by the combination of two samples. So this is not a simple Markovian assumption, but we still say that second order Markovian. And this is a Markovian. And this sometimes we call zerogram, unigram. This is a simple IID, if you know the word, identically independent distributed samples. Every time you sample, the probability distributions are same, regardless of n. That is the idea of the unigram. So how do we calculate these probabilities? That is the final topic. And again, I'm gonna be very quick. Actually, this is very interesting mathematical, development to estimate the bigram or unigram. But in short, you just count. You just count the occurrence. And and just calculate the ratio of the occurrence. Say that you have observed 1 million words, and out of that, you have observed the particular sequence of two words, say D map, for example, D map. These two words happened in the 1 million words text, say 100 times. Then the bigram probability, a bigram occurrence is like that. And you can calculate the number of the occurrence of the D. Suppose that you have 5,000 occurrence, no, not more, 10,000 of occurrence you saw. And out of that, 500, what did I say? 100 had followed by 100 D are followed by the word map. Therefore, the probability of the map followed by D, probability of the map following D is 10,100. So 100 over 10,000. That is the bigram probability. Actually, this is mathematically too, in terms of the maximum likelihood estimate. But I don't, I don't say much about that. But again, crucially important thing is that your observation is limited. So even though the probability is not zero, in some context you do not see that particular realization, which means that your estimate of the probability of such realization becomes zero. So do anyone calculate the probability of the dice? 1, 2, 3, 4, 5, 6. We all know that all of those probabilities are 1 over 6. But try slow 5 times, and you get 5 different numbers. You do not conclude that each dice probability is 1 over 5. But sometimes such things happen, like this. We have a lot of variation or realization of random variable, but unfortunately, in training data, you don't see these number of these realizations. So what we do is somehow discounting the occurrence of the data and distribute discounting into the unseen data. This is a very good way to extrapolate the probability, and this gives you a very reasonable guess of the probability of the unseen data. So this is a small topic or kind of a tip. But if you are interested in this idea, please look into the Google and search for the word probability interpolation, or things like that. What do we call? Okay, sorry. Again, final part is quite kind of rush. But I used 1.5. So I'm almost concluding my lecture. But I have talked about denoising. That is very important for dealing with the real data. And also, I wanted to talk about modeling the signal, modeling the data. And what I want to emphasize again is that calculating or solving solving for the optimal parameter of the model is not difficult. They do that. But hypothesizing the true rule or model against to the given data is up to you. So that is your mission. That is your skill. So please be more sensitive to the data. And I like you to be a person to try again and again and try to use more data, a lot of data, as much as possible. That is always good idea from my experience. Okay, thank you very much. Any questions or so forth? No? Oh.
In generalized regression model, how to determine A1 to AN? I don't know.
Which slide? Generalized.
Generalized linear regression.
Mm-hmm. Here? Okay. Okay.
In this
Ah.
regression, you have A0 to AN.
Yeah. I use the symbol A, but this is completely same with theta. So you can follow the discussion that I showed you in the third slide. So please think that this is that and this is that, okay? Then you can use this formula, okay? So in this case, in your case, theta 1 is x0, and here you use the value x0 m's power to m, and also here is the x n minus 1 power to m, okay? And organize this matrix, and then you can get the optimal theta. Okay? You're still not clear? Okay. Then we can discuss later offline. Other questions?
One
What?
Lambda in regulation.
Lambda.
Yes, in regulation form.
Do you mean? Do you mean this?
Yes.
And your question is how to determine the value of lambda?
Yes.
No one knows. We need to try.
Try what?
Try to confirm or search for the best lambda for your test data.
Okay, the next slide, there is
Two
2 lambda.
lambdas?
Yeah, lambda equals 0.
Yeah.
Then lambda is equal 0, and then lambda is equal -15.
Yeah.
How would they predict it?
Yeah, actually, this is always the case that you try several lambda values, blah, 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 and measure the performance by using the evaluation test set. And, what you see is like this, and you conclude that somewhere here or there may be best. But you still have open problems because you need to use that model to the different data. Therefore, you are not quite clear about that. Okay, AI or machine learning has limitation like that. We can build a very good system for your training data, but no one assures that that data works real well everywhere. Say autonomous driving vehicle trained in Japan, I don't know, does that work very good in Malaysia or India, because the data is completely different. So as far as you discuss about the machine learning like this, there's an open problem. So I'm sorry. But this is the reality. Okay. Other questions? Okay. Okay, thank you very much for coming. You sure?
When we construct the X in the solution to the linear prediction,
Mm-hmm. Mm-hmm. No. This one? This one?
Yes, yes.
Mm-hmm.
How can we construct X transpose, for example, X3, before we predict it? For example, the second column of X transpose is X3, X2, X1. So how can we know the X3 before we predict it?
Yeah, that's a very good question. Okay, there are two ways of answering your question. First answer is that we can use this to predict the value of xn. Okay, if you are thinking about predicting large x capital N, then everything is a past. So you have all data already, right? So there's one way of answering to your question. But the other way of answering your question is that our final target or our primary motivation is not predict, but understanding the nature of the signal, okay? Or in other words, identifying the model parameters. Therefore, knowing this system sometimes is the final goal for doing such analysis. Actually, in the speech coding, in the completion of speech, we use this method fundamentally and calculate these values and transmit these values instead of transmit speech itself. Okay? Because we have a very long speech segment, capital N, but what we need to send or characterize that speech characteristic is only 3 parameters. So we can reduce the size of the data based on the fundamental characteristics of the data. that was a fundamental principle of the cellular phone, invented in 1960s here in Nagoya University, LPC analysis, done by Professor Itakura. He's my boss. He was my boss. And, so so that's my second question, answer. Does it make sense to you? No? Not that clear? So I understand that your question is how to predict n, or how to use this, how to organize this matrix because of the, from the observation. No?
When we constructing the X, for example, we need to use X-ray.
X,
But X-ray is predicted from the X.
X3 is what?
X-ray is predicted from X.
X2? Well,
The
X,
X-ray is in the Y, the first entry of Y.
Y. Here, yeah.
So, and X-ray is the prediction, right? So how can we construct the X before we predict it?
Well, okay, to be more simple, let's say capital N is 10, okay? So we have a 2 to 8, 1 to 7, 0 to 6, and 3 to 7, 0 to something like that. All those samples have been already observed when you are at time 11. Okay? So let's start organizing this matrix when the time is 11. Then, putting those values onto this form is very simple, right? Okay. Okay, thank you very much.